All right. Great. All right. Hello, everyone. Welcome back to the course. All right. Are there people here? Yes. Okay. There's people here. Okay. So maybe fewer than usual because the assignment is due. Okay. So last time we were, okay. Someone says hello. If there's any problems, if you can't hear me or see me or something, say something in the chat. Okay, we are here. Yes, thank you for being here. Great. Okay, so we were in the middle of the type system, right? We were looking at the type rules for Java or the type rules for Juice, and I was giving you rule after rule after rule, and then we had a little break, and I talked about what you do with these rules, how you implement type checking in your compiler. And sort of the high level point there was that how exactly you do type checking depends on your language. It depends on the set of rules that you have. But in the case of these rules that I'm giving you for Juice, the type checking is fairly straightforward. You just follow the rules. And the basic idea is, whatever statement or expression you are given, you always look for a rule that has that statement. So if you get an if statement, say, you look for a rule that has an if statement at the bottom, or if you get an addition expression, you look for a rule that has an addition expression at the bottom. Okay. Yeah. All right. So I just should continue with rules for more Java features today. And where's my eraser? Here we go. Okay. So what other features are there? And so we can look at fields. All right, so classes have fields, and you can read them and write them. And fields can be static or instance fields. So I'm going to look at reading a static field first. And I'm going to say, let's say you have d.f is your expression. So here f is a field. D is some class, and you want to know, what the type of this is. So this is an expression that reads field f. It has to be a static field because you're calling f, or you're accessing f on a class. And so, to type check it, or if you see an expression like this, what do? Well, the obvious thing is to look in class D. Right, you're being asked for a field in class D, and I use the contain set of D. Right, so the field could be inherited from a superclass, and so you're looking for a field in D named F, and it had better be a static field. Right, so you want a static field with a type declaration and the name F, and if you find that field, then then the declaration tells you the type. Okay, so the type of the read is tau. Okay, and yeah. All right, so that's for a static field. If there's questions, stop me. But now, what if we read an instance field? And so that's going to look like e.f, where e is some expression. And we want to know, the type that we get by reading field f. Okay, and so since we're calling the field on an expression now, not on a class, we first need to type check the expression. So I'm going to go and recursively type check the expression. And now I hope that the expression has a class type, right? So I'm going to call that D. If the expression has a primitive type like int, then int doesn't have any fields. So then you wouldn't be able to apply this rule. You wouldn't give any type to this expression. And if there's no type for an expression, that's a compile error. Okay, so we type check the expression E. We get some class D, and then we look for the field in that class D. So as before, we're going to look for a declaration with a type and a field name, F. The field has to be named F. And we're going to look in the contain set of D. Right? Okay, and so if there's a field, it has type tau, then this tells us that if we read that field, we will get a value of type tau. Okay, so that's reading fields, static fields, and instance fields. So we can move on to writing fields, but any questions about reading fields? Okay, all right. So what does a field store look like? Well, let's do a store to a static field first. It's a little bit simpler. So if I have, so it looks like an assignment statement. And so on Monday, we had assignment statements where we were assigning to variables. In this case, it has a field expression on the left-hand side of the assignment. And we have some expression that we evaluate, and we're storing its value into field F of class D. And because, again, we're calling F on a class, it has to be a static field. Right? So we're going to look for the static field in class D as before. So static tau F in the contain set of D. Okay, and so now the type. Okay, I should have saved some more space here. Okay, shoot. All right, I'm gonna make some space over here. All right. So static tau F. Right. Okay. So we also need to type check the expression, and we're going to need to make sure that the type of the expression matches the type of the field. Right. So I'm going to also type check the expression, and it has some tau. Let's call that tau 2. And I can call the type of the field tau 1. All right, so I type check the expression. And now I need tau 2 to be assignable to tau 1. Right, so this is the same assignability check that we had for writing to variables. So if you implement assignability, when you're doing variables, you can reuse it here. Okay. So tau 2, the type of the expression, tau 1, the type of the field. And then the only thing that's left is that the assignment expression itself is also an expression. It's not just a statement. So you can use it as an expression. It has a value. And the spec says that it gets the type of the field. Right, so the tau 1 rather than the tau 2, the type of the expression. Okay, and that they could be different types, right? They just have to be assignable to each other. Okay, and then we'll do the instance field case of this. Stop me if there's questions. All right, so this time I'll leave more space. So in the instance field, we're writing to a field of an expression. That expression is going to evaluate to an object. And we have expression E2, which is what we evaluate to get the value to write to the field. So, all right. So here we're going to require, or we're going to type check both expressions. And once again, the expression E1 had better have a class type so that it can have a field. And then we want to find a field that's contained in that class. So we want to find a declaration of a field named F in the contained set of D. Okay, and then that tells us the type of objects that we're allowed to store in that field. And I'll put like a dotted line to separate us from the rule above. Okay, and what else do we do? Well, we type check E2. So E2 has to have some type, and we'll call that tau2. And then just like before, we need the assignability check, right? That something or a value of type tau2 is allowed to be assigned to a variable or a field of type tau1. Okay, and so that's the rules for fields. Any questions or comments or anything? Okay, so you know, I mean, the rules get a few extra premises, but they sort of all make sense. And the premises tell you, you know, what you need to check in your compiler, right? So when you go to implement these, if you see a field read, whether it's static or a read or write or static or instance field, you know, this tells you what to check. Okay, so all good for fields. Okay. So yeah, now my board's messed up. Okay, so all right, let me do the next thing over here. So next I want to talk about cast expressions, and you know, they're slightly somewhat of an obscure expression, but they're important in the Java spec because the spec defines a whole bunch of other things in terms of how you type casts. So, you know, let's look at typing casts. And the rules here are in section 5.5. Okay, and so a cast looks like this, right? You have a type in brackets, and then you have some expression, and basically you're evaluating that expression and casting it to the type tau2. So, okay, I guess, you know, the result is going to have type tau2, right? That's the whole point of a cast, to give you something with the type that you say it is. And now, you know, what should the premises be, right? What should E be? Well, first of all, you have to make sure that E type checks with some type. So, you know, remember I said last time, in any expression, you always want to type check all the sub-expressions, right? So you want to type check E recursively. Here you want to make sure you type check E1 and E2, and so on. Okay, and then one type of cast that's always allowed are casts between numeric types. So tau1. So if both tau1 and tau2 are numeric, right? So it's things like ints and shorts and bytes and chars. Then you're allowed to cast between them, you know, between any pair of numeric types. So we looked last week, I guess, about at assignability, or maybe it was Monday. I don't know. So we looked at assignability, and there the idea was that you're only allowed to do widening conversions, which are ones that don't lose information. So from a smaller number of bits to a larger number of bits. If you put an explicit cast, then even in JUICE you can do a narrowing conversion. So something that loses information where you have to throw out some of the bits. Okay, but so in JUICE the cast is required in that case. Okay, so that's casts for numeric types. And so then, what about for class types? And how about I do that? I want to give myself lots of room. All right, so, well, okay, I'll do it down here. So what if I cast an expression to some class type like C2? Okay. So what do I do? Well, again, I'm going to type check E1, and it's going to have a type tau1. Sorry, it's not E1, it's just E. It has, or I hope it has some type tau1. And in this case, tau1 has to be a class type, right? So the first thing that's not allowed is to cast an expression of a primitive type to a class type or vice versa, right? So this has to be another class type. And now, okay, what about relationships between C1 and C2? Well, okay, so there's a bunch of relationships, but the basic rules are either. So let's do it over here. So either C1 is a subtype of C2, and I'm going to say or C2 is a subtype of C1. Okay, so the basic rule is one of these two things has to be true, and I just want to kind of draw these. So if you think of the class hierarchy, right? So, and I like drawing triangles, right? We had triangles for parsing, for parse trees. Now the triangle is the class hierarchy, right? You've got object at the root, and then you have subclasses underneath. Okay, and so one type of cast is an upcast, where I have an expression. So here C2 would be down here. So okay, I'll do a bigger triangle here. Right, so C2 would be here, C1 would be here, and it's an upcast because the arrow goes upwards. You're casting upwards in the hierarchy. Now, the expression has the static type C2, which means that dynamically, the actual type of the value that you get in E can be any subclass of C2, right? So anything in this little triangle, and now you're casting it and you're saying, I want something in the bigger triangle above it. So this kind of a cast always succeeds. So it's an upcast, and I'm gonna erase this just so it's not in the way. So an upcast always succeeds. And so this happens when C2 is a subtype of C1. So I'll just draw a little arrow here to indicate that that's the upcast case. Okay, so you're allowed to do this. It might seem kind of pointless, but because, I mean, anywhere that you can use a C2, you can always, if you have a C2, you can use it in any context that requires a C1. So I mean, it's sort of pointless, but it's also harmless, and so Java allows it. And we're going to see in Juice, it's actually not pointless in a few cases. So we'll see that when we get to methods. Okay, sort of the more useful cast is a downcast. So again, well, here, I'll make it bigger. All right, so, all right, a downcast. All right, so now C2 is up here, C1 is up here, and basically, you're saying my actual type is anywhere inside the big triangle, and you are claiming, you're trying to tell the type system, I know more than you do. I know that my actual type is in this little triangle down here. So it's a downcast. Even though the best thing that the type system could prove is that the actual type is in the big triangle. Okay, so this is a downcast. And all right, and so the type system will trust you, but it will put in a runtime check to make sure that the dynamic type, right? So remember dynamic types and tagging the actual values, adding a little tag to the value to say this is my actual dynamic type. So we'll check that it really is within that small triangle there. So for a downcast, we're going to need a runtime check of the dynamic type. So this is where the things get a bit dynamic, right? We're mostly talking about static type rules, but we've got a downcast. Okay, and so these two are allowed. What happens if neither of these two hold, right? If you don't have an upcast or a downcast, so neither class is a subclass of the other. So, in the diagram, it kind of looks like this, right? And so you would have C1 and C2, and you're casting sort of sideways. And sometimes that's called a bad cast. And it's bad because it always fails. So fails. Okay, so if you had a cast like this where the classes were not one was not a subclass of each other, this class is always going to fail at runtime. And so, why did you write it in the first place, right? So this is something that the compiler is going to reject because, probably if you wrote this cast, you didn't mean it because it's going to fail every time at runtime. Okay, and so this is Java already rejects this cast statically. Okay, but there's an exception. So what's the exception? When can this not fail? All right. Well, okay, and I know there's a lag, so maybe like everyone's answering it, and the answers are going to come in a little bit, or maybe nobody's answering. I don't know. So numeric. So for numeric types, we have this other rule where numeric types are always allowed to be cast. So integers and shorts. No. Those. So the kind of the relationship between sort of the integer class and the int primitive type, and the short class and the short primitive type, that only came in later versions of Java, I think Java 5. But no, so we've got interfaces. Yes, so thank you. Yes, so interfaces are the catch or the tricky case. Okay, and so the thing with interfaces, right, is if I have, say, an interface 1 and an interface 2, and let's say these two interfaces are not related, so I've drawn them like beside each other. So the interfaces are not related, but they can overlap because I can define some class, so I'll call it C, that implements both interfaces. Okay, and so now if I have a class that implements both interfaces, then I'm going to, maybe I have an object of that class. I know statically that it's somewhere within, this left triangle, and now I'm casting it to the right triangle, and so I'm basically saying it's somewhere in the intersection here. Okay. So so with interfaces, this is the cast might not fail, and so Java does allow it statically. So I'm kind of going to add an extra case here to say so C1 and C2 both interfaces. Okay, so if C1 and C2 are both interfaces, then this should succeed, or this should be allowed. And then, in fact, there's one more case, which is if you have one interface, if you have an interface and a class, right? So let's see. So I have an interface. Let me draw it smaller. So I have an interface and I have a class, and those interfaces or the interface and the class are not related, right? But I mean, it's still possible for the interface and the class to intersect, and for me to then declare another subclass, so a subclass of the class that also implements the interface, right? Even if the superclass didn't implement the interface, a subclass of that class can additionally implement the interface. So I'm going to say, or sort of one interface and one non-final class. There we go. Okay. So the non-final is actually in the spec. So you might say, well, if the class C was final, then there's nothing underneath it, right? There's no subclasses. And if a final class C doesn't implement the interface, then you can't subclass the final class with a class that would implement the interface. So basically, if one of C1 or C2 is a final class and the other one is an interface, then it's also allowed. So these are the cases, and you can see like it's somewhat subtle what the list of all the possible cases are. But the idea is that the spec is trying to rule out casts that are guaranteed to always fail no matter what. And the ones with interfaces, it can't be sure, right? Because you could always create a new class somewhere that's going to implement both interfaces. Now, I suppose with Juice, we could be even more strict, right? Because in JUICE, we give you the set of all the possible classes on the command line. And so you know all the classes in the entire program. So in JUICE, you could actually check to see, like, hey, is there a class that implements both interfaces? And if there isn't, then the cast is guaranteed to fail. But in Java, there isn't this notion of having the whole program and sort of knowing, okay, the program consists of only these classes and no more classes. Java sort of wants to be open to adding additional classes to an existing program, right? You can take like a library and override parts of it with new classes. That's sort of part of the object-oriented philosophy, right? Of being able to subclass an existing class to change its behavior. So in Java, we don't know whether someone is going to later create a class that happens to be a subclass or happens to implement both interfaces. Okay, so question. Okay, all right. So let's see. So once you have casts, now there's two other features that kind of depend on casts. And so one of these is the instance of check. So this is kind of like the check that you do as part of a cast. But if you want to do the check without making sure that it's going to succeed, right? A cast, if E is not a subtype of tau2, it's going to fail and throw an exception. But if you think it may or may not be of that type, you can use instance of. So I'm going to say if I have some expression, and you can say instance of C. Okay, and I'm going to say instance of C2. Okay, and so as always, we're going to type check E. So we're going to see what the type of E is. And again, so in this case, it had better be a class type. And then, when are you allowed, what is the relationship between C1 and C2? Well, the spec says it's exactly when you're allowed to do the cast, right? So what I'm going to do here is a little bit of a weird thing. I'm going to say, if a hypothetical cast of E to the type C2 would succeed, or not would succeed, but would be statically type correct, right? So if the type system allows you to cast an expression E to the type C2, then you're allowed to do the instance of check. So that's kind of, you would have to go back to this rule to check this premise. You can, of course, implement it by taking the premises of this rule and inlining them into here. But the way it's phrased in the spec, right? So in the spec, they give all the details for casts, and then for instance of, they say, well, the rules are the same as for casts. So I'm writing it this way to say, it's like a cast. But the weird, the weird thing about this rule is that, here I've written a piece of syntax that doesn't appear anywhere in your program, right? The program that you're type checking doesn't actually have an expression E being cast to type C2, all right? So I suppose you could implement it like the rule says by creating a piece of AST where you put that cast and you try to type check it and you make sure that it does type check. But probably a simpler way to actually implement this rule is to take these conditions and just copy them to be premises of this rule. Okay, so instance of is allowed in the same cases as a cast, but only for class types, so not for numeric types. And if it's allowed, then the type of instance of is Boolean, right? Because it returns true or false. Like is E's dynamic type, actually a subtype of C2. Okay, so that's cast an instance of, and then there's one more feature that is like instance of in terms of being defined in terms of casts. And that's equality comparisons. Okay, so if I have E1 equals E2, or E1 not equal E2. Okay, and so the question is, when am I allowed to compare two things for equality? And, again, you might think, well, always, like either they're equal or they're not. But again, Java tries to sort of help you or protect you from bugs by saying, okay, we're only going to let you compare them if it's possible that they could be equal, right? If E1 and E2 are definitely different, and you can prove that at compile time, then this is always going to be false. I guess this one's always going to be false. This one's always going to be true. And in that case, like, why are you writing the condition, right? It's probably a bug, even though, I don't know. I mean, maybe you really wanted to write, true this way or whatever. But, okay. So if it's all, so as before, we always type check E1 and E2. So we make sure that they have some types, tau1 and tau2. And then, like here, you're allowed to compare them if you would be allowed to cast them. So, and I'm going to say, let's say E2, I'm allowed to cast to tau2. So if I'm allowed to cast, E2 is already of type tau2, so I want to cast E2 to tau1. Okay, so if you would be allowed to cast one expression to the other, and the Java specs actually says if you could cast E2 to tau1 or E1 to tau2. So it says to try both directions, but the rules here are for allowing casts are symmetric. So so if you implement these rules here, right? They're symmetric here. They're symmetric here. They're supposed to be both numeric types. Okay, so for juice, one direction should be sufficient because the rules are symmetric. Okay, and then in these cases, of course, the equality comparisons give you a Boolean result. Okay. Oh, and I'm just abusing notation here a little bit by writing two different conclusions, below the line, and that just means, if I wanted to write things out in full, I would have two rules, one with this conclusion, one with this conclusion, but they have the same premises. Okay, so that is comparisons. I'm just looking at space. Right. All right. So can you cast an integer class to the int primitive? And can they be checked for equality? So in Java 1.3, no. I guess the rules are separate between primitive types or numeric types and class types. So you can't cast between them. The integer class has, I think it's called int value or some sort of method that gives you that primitive, and another method that translates in the opposite direction, but you can't cast between them. Starting from Java 5, the language got an auto boxing feature where if you use something of type integer in a place where you need something of type int, it will insert such conversions or such method calls automatically for you. And so, then you can do such things, right, using an int where you need an integer or vice versa. But that's only in later versions of Java. So that that doesn't affect us for Juice. And it, it obviously complicates things, right? The compiler has to know what types it wants, and it has to insert those conversions at the right places. Okay, so the next feature I want to look at are methods. So method invocation or method calls. Okay, and I had fields before. So let me start with a static method. And let's see, how much space am I going to need? All right, how about like this? So if I call a method on a class, so again, I'm going to use D for my class. And the method call, can have some list of argument expressions. Okay, and I'm trying to type check this method call. Okay, well, so like with a field, I'm going to go into the class D, and I'm going to look for a method with that name. And I'm going to be looking for a static method. And the declaration of the method will give me a return type for that method. Right? And the method declaration also has a list of parameter types. And this should be in the contain set of D. Okay, and I gotta erase stuff to okay. All right, so I'm going to find this method in the contain set of D. So it could be, inherited from above or whatever. Okay, and so the method declaration, it tells me the types of the parameters. It tells me the return type. So, as I always say for all the rules, I always have to type check all the sub-expressions. So I need to type check the EIs. So I'm going to say for all I, and I want to type check EI. And I want to make sure that EI has the type tau I. So each expression has the type that is in that position in the parameter types. Okay, and so if that's the case, then this is the method that I'm going to be calling. So then I get my return type tau is going to be the value of the method call, right? Whatever the method returns, that's the type of the method call expression. And so now one thing that is sort of specific to JUICE is that the exact type of the expression, has to exactly match the parameter type in the method declaration. So, for example, if I have a method that's declared to take an object type, and I pass it a string, then you would expect that a string is an object, and so you can use a string anywhere that you need an object. But in JUICE, we're going to say no, because so we're going to say no. So we're not allowed to pass a string to a method that requires an object. And if you have a string and you want to pass it to a method that requires an object, you can always upcast it, right? We have the upcast, and that's the cast that always succeeds. So, I write my string, I upcast it to object, and then I can pass it to a method that expects an object, and the upcast will always succeed. So, it's a workaround that will always work. But okay, so you can always do this, and in JUICE you need to do this. But why are we making you restricting JUICE that way, right? So I'm going to say JUICE so requires an exact match, and so I guess it's what this rule says, right? The actual type of EI has to be exactly tau I. And in Java, there is a complicated set of rules to find the closest match. And it's in JLS 15.12.2, right? So, you can look there for the rules that Java uses, and they are quite complicated, right? And, why are they complicated? Well, because of method overloading. So the contained set of D could have multiple methods, all with the name M. And so, for example, you might have one method that takes an object and another method that takes a string, both with the same name. And so, which one do you pick if you pass a string? Both are sort of eligible to deal with strings, but the closest match, is going to tell you, okay, you should take the string method, right? Because that's sort of more specific. But, then, okay, maybe that's still not too complicated a rule. But, then what happens if you have a method that takes two parameters, right? And, maybe you have one parameter that takes an object and a string, and another method that takes a string followed by an object, and then you pass it two strings. So, which one's the closest match? Well, in that case, it's ambiguous. Neither is closer than the other, and you get a compile time error. But, what if you had object and object string? There's all sorts of cases that you have to deal with. So, it is, it's not impossible to implement the rules, and they are laid out here. But, this is sort of one of the especially annoying parts of Java to implement. And so for the project, I want to spare you from that annoying implementation. And so that's why Juice requires the exact match, right? So you type check E1, whatever type you get, that has to be the exact type that was in the declared signature of the method. And if it's not, if you want the workaround, you have to put in the upcast. Okay. And why is it there? Well, it's really just to make your lives easier. And I know, maybe you're surprised, like the compiler is already a lot of work, and there's various things in there that do seem complicated, or like a lot of stuff to implement. Some things in Java are just, I always kind of weigh the educational aspect, right? Does this teach you anything versus, how much code it is to implement, and how much pain it is to debug. Okay, so for Java, we would have to encode the rules from this part of the spec in, way more complicated rules to specify a method call. For Juice, we just have this. If there's questions, ask questions. But in the meantime, I'm going to do instance methods, right, which are non-static methods. And I guess I have space. So I'll go here. So those are ones that I call on an expression. And there's nothing too surprising here. I'm going to type check my expression. Whoops. And I want to make sure that my expression has a class type D. Okay, and my method call has arguments as before. Okay, and so the only difference is, well, I mean, I'm still looking for a method. This time it's a non-static method, but I'm still looking for it in the contain set of class D. All right, so I look in the contain set of class D for a method with name M, and that's going to tell me the return type. So the return type is tau, and then I have the same check for the arguments having the correct parameter types. Okay, so again, these types, the tau I, have to be exactly the same types as the parameter types in the method declaration. I want to say, like, in terms of what features Juice does have and doesn't have, like Juice does allow you to have method overloading, right? So, that is I guess you could say it's educational to try to implement a method overloading. So, lots of languages do have the ability to have multiple methods with the same name in a class, but just the closest match rules are a bit too much of a pain. Okay, so you could still have two or more methods with the same name, and then you would pick the right one based on the list of argument types. Okay, so stop me if there's questions, but I'm going to move on. So when you call a method, okay, good. And so now you're in a method, and you need to return, right? And so in Java, there's two forms of the return statement. So return is a statement. So we're not going to have a type here. But when are you allowed to write return with no return value, right? So there's return, and then there's return some expression, right? So those are the two forms of the return statement. And okay, and so the way that you know which one of these two forms is allowed is depending on what method you're in, right? If you're in a method whose return type is void, then you have to say return with no expression. And if it's not void, then you have to give an expression. Okay, and I mean, it was a while ago, you might not remember, but in the context that we have for type checking, one of the three elements is the return type of the current method, and that's that third one. So if the return type of the current method is void, then you're allowed to say return. And if it's not void, well, then it's going to be some type, and let's say sigma. Okay, and so if the type is sigma, you're going to have to return some expression, and I'm going to type check the expression, right, with the same context, and I'm going to get some type. Okay, and it could be a different type than the return type, but it has to be assignable to the return type. So I'm going to say, I'm allowed to assign tau to sigma. Okay, and so the way that return is implemented, right, it's kind of like an assignment, right? You evaluate the expression and you get some value of type tau, and then, well, I mean, I don't know, you're not really assigning it to a variable, but you're passing it back to the caller, and the caller is expecting something of type sigma, and so if tau is assignable to sigma, then whatever value you have, also works as a sigma. Okay, so method calls, returns from methods. All right, again, stop me if there's questions. And I've got one more feature that's kind of related to methods and method calls, and that's a constructor. A constructor call, like an object creation. I mean, it's different in that it creates a new object, whereas calling a method just calls the method. But an object creation, always calls a constructor. So it's like two operations in one, right? It creates a new object, and then it calls a constructor. And so therefore, the type checking for it is a lot like the type checking for methods. So I'm going to say, if I have a new, and I'm constructing some class D, right? It had better be a class type. And then I'm allowed to pass arguments to the constructor. So we'll call them E1 up to EK. Now, I know that the type of this object creation is going to be D, because I said I wanted an object of type D. And now I just need to find the right constructor, right? So, up here, as with methods, I'm going to type check all of my arguments. So EI has some type tau I. Okay, so I type check the arguments, and then I'm going to look for a constructor in that class that, again, whose parameter list has the same types as these tau i's. So I'm looking for a constructor, and a constructor, looks like this, right? Its name is the class name, and again, I'm looking for a constructor whose parameter types are exactly tau1 to tau k, and that constructor, I'm going to say it's in the declare set of class D. I mean, when you're creating the declare sets, okay, maybe I shouldn't say it's in the declare sets, right? Because when you're creating the declare sets, you only want to put methods and fields in them and not really constructors. So I guess the important thing that I was trying to highlight is that you're not looking in the contain set for D. In other words, constructors are never inherited, right? So constructors are always in a particular class, in the class in which they are actually declared. And so you have to look exactly in the class D. You don't bother looking for constructors in superclasses or anything like that. Okay, and as with methods, we do an exact match for juice, and Java would do the same closest match for choosing from an overloaded constructor, right? So a class can have any number of constructors, and so you want to choose the one that matches the types of the arguments that you pass in. Okay, so constructors are type checked, very similarly to methods. I guess I can, you can kind of compare this to this, right? It's a similar rule for constructors. Okay, so let me pause for questions. And I've got one more feature of Java to type check. It is a pretty nasty feature, but okay, but we've got almost 20 minutes, so perfect. So this is hopefully we can finish the last feature of Java that we need to type check. So what haven't we type checked yet? Well, arrays, right? So arrays have some weird and interesting aspects to them. Okay, so I guess the basic rules for reading and writing from an array, they start out a little bit like fields, like field reads and field writes, in that. Okay, so what does an array read look like, right? I have an expression, and then I have square brackets, and I have some expression, inside the square brackets, and I want to type check this. What was I going to say? Sorry. Right. So I mean, it's kind of like a read from a field in that you have an expression and you're reading from something in the expression. Sort of the difference is that, when you're reading a field out of an object, you just have the object and then the name of the field. Whereas here you have two expressions, right? There's the index expression. So, all right. As always, we're going to type check both expressions. And now the type of expression one has to be an array type. So I'm going to write this as tau1 with square brackets to say that, that the type of E1 has to be an array of something, that something is tau1, but it has to be an array type, right? If you get int or string for E1, then this rule is not going to apply, and the array read is not going to type check. And then we're going to type check E2, and we're going to get tau2. And then the rule is that tau2 has to be a numeric type. Right, so the tau 2 is the type of the index expression, and so that has to be a numeric type. Typically, usually it's an int, but it could be, it's allowed to be like a char or a short or whatever, and at runtime Java will just convert it to an int before it does the array access. Okay, and the array read is an expression, so we need a type for it. So the type of the element that you get out of the array is tau1, right? If it's an array of tau1s, then an element that you read out of it is of type tau1. Okay, so I mean, this rule is hopefully not too surprising. I mean, if it is, do ask questions, but reading out of the array. Then for writing to an array, we're going to have an array store expression that's going to be, it's a little bit like when we were writing to a field. It's an assignment with an array expression on its left-hand side. We had assignments with variables, then we had assignments with fields on the left-hand side, and now we have assignments with arrays. So we're going to separate things. So, what are we going to do? Well, we're going to type check the three expressions, the three sub-expressions, right? So E1, again, had better have an array type, right? So we'll say tau1 with square brackets, an array of tau1s. E2 needs to have a numeric type. Oops. So tau2, tau2 has to be a numeric type, just like above. And, the only difference now is we also have the expression E3 that needs to have some type. We will call that tau3. And then we want a value of type tau3 to be assignable to a location of type tau1, right? So it's an array of tau1s, and so each element of the array is of type tau1. So tau3 has to be assignable to tau1. Okay, so again, there's a whole bunch of premises, but they shouldn't be, they shouldn't be scary. Okay, so what else? What else is there about arrays? So we read from an array element, we write to an array element. One other thing you can do to an array element is read its length field. Okay, so if I have an array, even though it's not a class type, so it sort of shouldn't really have fields. But if the type of E is an array type, then you are allowed to read this special field length out of it, and you will get an int back, right? And that tells you the size of the array. And what else is there with arrays? Well, we want to be able to create arrays. All right, and so the way that you create a new array is with the new operator, and you give a type, and then you give an expression to say how many elements you want in the array. And that will create, a new array of tau1s with, E many tau1s, right? So what do we have to check here? Well, one interesting thing is that tau1 can be any type, but so you can have an array of ints or an array of classes or whatever. But of course, the expression E has to be of a numeric type. So we'll say it's of type tau2, and that has to be a numeric type. So, I mean, you could use a character, to say how many elements of your array there should be. I think it's pretty uncommon for someone to say, I want, X elements, but I suppose it's allowed. But, typically tau2 would be int. Okay, and so that's what you have to check, right? That you have an integer as the size of your array, and then the type of the array creation expression is an array of tau1s. So tau1 array. Okay, so I mean, there's nothing, or there shouldn't be anything too surprising in these rules. The one thing that I keep forgetting to mention is that in JUICE we only have one-dimensional arrays. Okay, so there are no multi-dimensional arrays in JUICE. There are in Java, but again, it's one of those things that just creates a lot of headaches, and I don't want to bother you with multi-dimensional arrays for the course. I suppose they would be educational, so there is that. Like, maybe they should be there. But perhaps if our semesters were longer and there was more time in the term to do the project, we would have multi-dimensional arrays. Okay, so no multi-dimensional arrays in JUICE. Every array is only a single dimension. So okay, so all of these are straightforward. So why am I saying that arrays are bad? And so they go a little bit weird when it comes to assignability. So array assignability. Okay, so what can you assign arrays to? Well, I can, if I have an array or an expression of an array type, of any array type, I can assign it to a variable that it has the type object. Okay, and so this is a little bit weird because normally if a variable has type object, you only expect it to have objects in it, and objects are things that have fields and methods. So this is going to be kind of painful when we go to implement code generation, because the way we generate code for arrays is going to have to be compatible with objects, right? So because you could take an array and put it in an object variable and then do stuff to it that you would normally do to an object, like read fields or call methods, and the object has to support that, okay, or downcast it or whatever. Okay, and the other weird thing is the Java spec also allows you to assign an array to to a variable whose type is Java lang clonable, or Java io.serializable. Okay, and basically the spec lists these three as the things that you can assign arrays to. So, I mean, they're a little weird, but no big deal. You just, implement what the spec tells you to, and you allow people to assign them to these things. They're mainly going to be annoying when we get to assignment 5 and code generation. Okay, but now, what about, when can I assign arrays to other arrays, right? What if I have an array of apples and I have a variable that requires an array of fruit? Can I assign an array of apples to an array of fruit variables, right? Is an array, is it true that an array of apples is an array of fruit? Okay, so I'm going to write down a rule that we had sort of at the very beginning when I first introduced assignability. And, back then I said that if I have two class types, okay, then I'm going to be allowed to assign an array of D. Sorry, not an array. If D is a subclass of C, then that means every object of class D is also an object of class C. So then I'm allowed to assign from an expression of class D to an expression of class C, right? And this assignment will always work because whatever object I get of class D, will also be an object of class C. Okay, so that's the rule I had just for assignment between class types. And so now the Java rule says, there's a different rule. I'm just doing this in red just because I want to emphasize that this rule, looks the same as the rule we had before, except for the square bracket. So in particular, the C and the D are in the same order as they were before. Okay, and this is, there's a technical term. This is called covariant subtyping, and if you're probably some of you are taking CS 442, and you probably discussed covariance and contravariance, and that's good. And everybody should take 442. It's a great course. You learn a lot of theory, and it's great. But just simply the co in covariance is just trying to say that the order of the C and the D is, it's the same order. And in particular, it's the same order as in the assignability rule between classes, where you had that D is assignable to C. So now we're going to say that a D array is assignable to a C array. Okay, so you can assign an array of apples to a variable that is supposed to hold an array of fruit. Okay, so why am I making such a big deal out of this, right? Of course, apples are fruit, and so if I have a bunch of apples, I have a bunch of fruit, right? So that should be fine. But it's not fine, right? It seems like it should be fine. But this rule, this is a rule in Java, so it is a rule in Juice, so we have to implement it. But this is a rule that makes the type system unsound. Okay, so unsound. Okay, and so it turns out that you can use this rule to take an apple and turn it into an orange, right? You can use this rule to take an object that so take an expression, let's say that is of type whose static type is orange, but you can get the value apple, right? You can create an apple object. You can say new apple, and do some tricks with arrays and with this rule, and get that object whose dynamic type is apple into a variable whose static type is orange. Okay, and I mean, I'm assuming apple and orange are not subtypes of each other, right? They're incomparable. So it's unsound. You can subvert the type system, right? Remember, the whole point of the type system was to make sure that if I say that my variable is of type orange, that at runtime, I will only ever have oranges in it. I will never accidentally find an apple in my variable of type orange. Okay, and now we're sort of at the end of the time, and maybe that's good, maybe that's bad. I'm going to leave it as an exercise to think about how you would exploit this rule, how you would write code that exploits this rule to, okay, and we've got yeah, almost. So I think you've got the first 2 lines of this code, and there's 1 or 2 more lines that you need to write. Okay, so if I leave it as an exercise and someone solves it right away. Anyway, you can think about, play around with arrays, and if you find a way to subvert the type system using this rule, try coding it up in Java, and try compiling it, see if it compiles, right? Does Java really allow it? And then see if it runs, and see if you can actually get an apple into an orange variable, or vice versa. You could get an orange into an apple variable. Okay, so try running it and see what happens. I will, tell you, give you an example in the next class on Monday, and we'll talk about, what Java does to mitigate this unsoundness, and sort of how it fixes this problem, and maybe why it has this rule. I guess why it has this rule is sort of obvious-ish, right? It seems like it should be the case that an array of apples really is an array of fruit, so you should be able to assign them this way. Okay, so I am going to need a few more minutes to really go over the example and the discussion of the example. So I'll leave that till Monday. Sorry to leave you hanging, but on the other hand, it'll give you something to think about until Monday. So yeah. So any final questions before we call it a day? All right. Yeah. All right. So you can think about arrays. We do have all the rules that we need to implement for arrays. So if you're implementing the type system, you've got all the rules that you need now, right? This is the right rule. It is a little bit of a weird rule, but this is the rule that you want to implement. Okay, no questions. 5, 4, 3, 2, 1. 5 seconds to think of questions. Okay, well, good luck finishing assignment 2 for those of you who aren't finished yet, and have a good couple of days, good weekend, and I will see you on Monday. Okay, bye.